Okay, I'm going to finish this paper that I went through. There's already 2 videos on this Edexcel International A-Level Physics paper on Unit 2, Waves and Electricity. It's the summer paper that students took. The reason I'm doing it now is because on Tuesday, 3 of my students are retaking Unit 2, and I know a lot of you on YouTube also wanted me to go through the final section of this paper. Okay, so the final section of this paper is questions 16, 17 and 18, and in particular people want to do question 18, so I'm going to go through them in order just in time for you to be able to prepare for your retake exam, or if you're doing it for the first time, it would be useful for you to have seen my answers. Okay, so I'm just doing it from my PDF, so I won't be able to do any handwriting on this paper. I'm just going to talk you through my pre-written answers. Okay, so the question 16, I did 2 videos before. Question 1 to 10, I think, was in the multiple choice section, has already been covered. It's been viewed by a reasonable number of students since last week. And I did questions 11 to 15, which were sort of shorter at the beginning of the structured questions, and now 16, 17 and 18 for the final one. So some of you have asked if I do private tuition. If you go to the YouTube channel and go to the home page, that's what you've got to look for. You will be able to contact me. There is contact details somewhere available. I think you've got to press on more. Okay, so that's one specific student asked me recently if I can help them with their preparation for physics. So I don't tend to do too many students like that, but if it can be arranged and it's mutually convenient to do that, I'm happy to do that. While I'm talking to you, please, if you haven't subscribed, make sure you subscribe so you see when new videos are uploaded. I do need to increase the scope, the reach of the channel to make it viable for me, because obviously it's a lot of extra work. And eventually, when we get to 1,000 subscribers, YouTube will actually pay me for giving them content. So I hope you can show your appreciation each time. Give me a like, share it with your friends so we get to be known. The channel has only started last January, so we already have over 500 subscribers. But for YouTube, they don't do anything until you've reached 1,000. Although when I watch it, they still are using advertising on my videos. So I don't know if you see videos or not. Anyway, that's just a plea for you to show your appreciation by liking, sharing, and subscribing to the channel. Okay. Also, if you go to the channel, you'll see that some people have said, can you also do the January paper? Well, the January paper is already done. To find them, you need to go to the home channel, click on playlists, and look for the playlist that you're interested in. For A-level, it's organized by the year of the exam. There was also a request to help students prepare for Unit 3. It's more difficult to help students prepare for Unit 3, but there are some Unit 3 papers. Unit 3 for International A-Level are the practical skills, so like uncertainties, treatment of errors. A lot of it's common sense, so it's actually you have to do the practicals to understand where they go wrong. There are 8 core practicals in year 12, 8 core practicals in year 13. There's also some Unit 6 ones, which is the equivalent in year 13 to Unit 3, and they are worth looking at in terms of understanding what the examiners want you to be able to talk about during the practical process. Okay, so if we have any in this exam talking about practical skills, I'll try to teach you the skills by doing the theory questions, okay? But there are some of the Unit 3 and Unit 6 questions available too. Okay, back to this paper, question 16. It's mentioning that there's a security lamp that switches on automatically, and I put when the brightness decreases, okay? So that's when you want it to switch on automatically. So obviously when it goes dark, they want the security lamp to go on. So when the intensity of the light on the LDR decreases, as a light-dependent resistor, so this is the symbol for the LDR. The arrows represent the light, this rectangle is the resistance, and the circle is used because usually the LDRs are round and they're made of a material which is energized by photons. So it's a photoelectric effect, in effect. And when it happens, when the brightness increases or the light intensity increases, more free electrons exist in this material. So it's a kind of semiconductor material which is energized by photons. But they want the light to come on when it gets dark. So imagine the light intensity decreases, the resistance of the LDR increases, okay? Because it has fewer electrons in the conduction band, okay? That's what you need to go and revise conduction band and the when they are already not free electrons, they're in the non-conduction band, so they're basically stuck in their atoms position. They can't move around freely. So part of the electric circuit in the security lamp is shown. The cell has negligible internal resistance. In reality, remember, cells have some internal resistance. What they're saying is don't worry about it for this case. They got two resistances dividing the potential difference that is provided by the EMF of the battery. So you don't have to worry about the third resistance, which is inside the cell. The light intensity on the LDR decreases. So imagine one of the arrows has disappeared. Yeah. Explain what happens to the potential difference across the fixed resistor. Yeah. Well, as the light intensity decreases, the resistance of the LDR changes. Yeah. Whereas the resistance of the fixed resistor is constant. Okay. So if this one increases its resistance, it's going to get a bigger share. Yeah. Potential dividers. Yeah, so these two resistors are basically potential dividers dividing the potential available to them, which is whatever this is. Say if this was 12 volts and this one gets a bigger resistance suddenly, it will now get a bigger ratio of the voltage compared to whatever it was getting when it was brighter. So as I put here, for the 2 marks, as the light intensity decreases, the resistance of the LDR increases, so the PD across the fixed resistor will decrease because it's a lower percentage. But they just want you to explain it in 2 points. And you could put because it's a potential divider circuit, okay? But that's all you need to put for the marks to be awarded. Part B. It says the security lamp switches on when the PD across the fixed resistor is 0.62 volts, okay? Across the fixed resistor. So remember, the fixed resistor will get 0.62 volts. That means the rest of the battery's EMF will go to the LDR at that point, okay? So the reason they put 0.62 volts is because normally that's when a diode switches on, and if you have a light emitting diode, that would be your security lamp switching on. When the lamp switches on, the ratio of the resistances of the LDR to the resistance of the fixed resistor is 3:2. Okay, that means at the point where the lamp switches on, the LDR has 1.5 times the resistance of the fixed resistor. Okay, and we know they've given us the current in the circuit as being 28 milliamps. Don't forget that's 28 times 10 to the minus 3 amps. So whenever you have these prefixes, make sure you've changed the units into standard form. They then want you to calculate the resistance of the LDR. Well, if we know that the LDR's resistance is 1.5 times the resistance of the fixed resistor, and we know that it's going to be 0.62 when it switches on, so the LDR must be 1.5 times 0.62 volts. Okay, so it gives you 0.93 volts for the voltage across the LDR. And since we know the current, we can work out the resistance of the LDR. Okay, so it's just a mathematical thing, and you'll get 33 ohms if you do it correctly as I've shown you. Okay. Question 17 is to do with photoelectric effect again, or is to do with photons. So in the second half of the 19th century, scientists began to investigate interactions between photons and electrons. Basically, they used voltage, to see what voltage did to gases. And if you put a high voltage across a gas, and this is how fluorescent lights work, the gas gets energized by the electricity, because remember, voltage is simply the amount of joules you give to charged particles, okay? And in the gas, there must be some charged particles because everything's made of atoms, and atoms are made of positive nuclei and negative electrons, okay? When the discharge tube is connected into an electric circuit, yeah, the gas emits photons, so it emits light. The photons have specific frequencies. One of the emitted photons has an energy of 3.44 times 10 to the minus 19 joules, yeah, and that means the energy is equal to h times F, where h is Planck's constant and is given to you in the list of constants in the back of the paper. Make sure you are familiar with all the constants at the back of the equation and when you've got to use them. So the first thing is to make sure you know you're going to use this equation. So since energy is equal to h times F, the frequency, you can work out the frequency knowing what the energy is, because h is a constant. Here is the value of the constant, okay? So you divide the energy that they tell you it is by the Planck's constant, and you'll get the frequency is 5.19 times 10 to the 14 hertz to 3 significant figures. Why are we giving 3 significant figures? Because we know the energy to 3 significant figures. And Planck's constant in your data sheet is also given to 3 significant figures. So you should really quote your answer to 3 significant figures. Once you go beyond that, they want you to do a qualitative answer, and let's go through it gradually so you don't see all my answers in one go. The electrical circuit applies a large potential difference, PD, across the discharge tube. Yeah? So from here to here, you've got a large voltage. Explain how the PD across the discharge tube causes photons to be emitted by the gas atom. So imagine the voltage is high, and imagine this side is positive and this side is negative. Well, the electrons will be attracted to this side, and if it's strong enough, the difference in the potential between this grass is you basically got an electric field across there, and it's going to rip off some of the electrons out of the atoms, or at least attract the electrons and give them something to be attracted to. So some of the electrons will be energized by that, and they'll escape the gas or move up in terms of their energy in the atom. So that's the basic concept, that the voltage provides the energy per unit coulomb. So a large PD causes a current to flow. This is how the examiner's done it. Yeah, a large PD causes a current to flow in the gas. In other words, for the current to flow, it must be separated into charges, positive and negative charges, because a current is the rate of flow of charge. So it must have ripped off some of the electrons out of the atoms. Okay, I put in brackets, voltage, remember, is joules per coulomb. Okay, so and current is coulombs per second. So energy is transferred by electrical work to the atoms in the gas. Okay, so that's 2 marks already. Then you say this energy, high PD, is sufficient, yeah, to move electrons in the atom to higher energy levels in the atoms. Remember that this is the electron levels that exist in all atoms and molecules. And these excited electrons will eventually fall back down each time they get energized if they're not completely ionized by the electric field. Okay, so these excited electrons will, if they're still in the atom, will be attracted to the ground state or to the lower, whichever energy level they came from. And each time they fall back down, and this will be a dynamic equilibrium, some will get excited, some will be de-excited, and each time there is a de-excitation, so a photon is emitted in the process. So now we've got 4 marking points that we can get. So the process of de-excitation is the process that emits the light, not the energization. The energization is putting the electrons into a level where they can then fall back down, and they will. Okay, what goes up must come down again. So different photons will be emitted corresponding to the energy level transitions which are available in the atom of the gas. It depends on the gas that you're using. For example, sodium gas will give you an orange appearing light, and therefore it will produce emissions of photons. So it's called an emission spectra or an emission spectrum for one. It will emit known frequencies for which are the fingerprint, if you like, as an analogy of the sodium atom. Okay, and you could do with mercury, you'll get different colors. Okay, so only specific energy levels exist in each atom, so only specific photon frequencies can be emitted according to the energy transitions available. I hope that makes sense to you. If it doesn't make sense to you, you need to go and revise the energy levels in atoms transition. So you can stop the video, have a look, and see how clearly you've explained your own answer. And they give you 4 marks for making these 6 bullet points, and then 2 marks based on what they think is your logic and how you've linked the points together. So I've spoken more than I've written, yeah, because I'm explaining it to you. And to explain is to really understand something, okay? And you've got to show your understanding by explaining things in a crystal clear fashion for the marks, okay? The exam question is still not finished, so there's a part B. So it says the photons emitted with this much energy, yeah, 4.75 electron volts. Remember before, they were given the energy in the last question in joules, yeah? This time they're given it in electron volts. Remember that E equals QV, energy equals charge times voltage. So here's a charge, E, here's the voltage. So 4.75 electron volts is a unit of energy. It's the amount of energy gained through putting like electrons through an acceleration of 4.75 volts. So I always tell my students, how do you accelerate an electron? You put a 4.75 volt plate in front of it and it's positive. The electron will be, in theory, accelerated to the 4.75 plus 4.75 volt plate. Okay, here they said the photons have this energy. Okay, so electron volts is simply another unit of energy used for small particles or small amounts of energy. Okay, so you need to know how to convert electron volts to joules and from joules to electron volts, and that's what they're testing you. So photons with this energy are instant on a metal surface, so we're basically talking about the photoelectric effect, yeah? So once we do that, the photoelectric effect, you need to understand what the photoelectric effect is, okay? These photons cause electrons to be emitted from the metal surface, which is the photoelectric effect. Here's the equation for the photoelectric effect. The incoming photon has an energy of HF. It needs a minimum amount of work to release the electron or get the electrons from inside the metal to the surface, and any difference between HF and phi will give you the kinetic energy of the emitted electrons, okay? So once you have that, the emitted electrons will have maximum kinetic energy depending if you have the HF maximized, and the surface, the electrons closest to the surface will need a minimum amount of this much energy. And this time they're giving it to joules, so they want you to be able to convert this into joules or vice versa, this one into electron volts. Okay, so show the maximum speed of the emitted electrons is about 5.3. So you've got to prove it's 5.3. You don't use this value, you get this value and show that your answer that you get is 5.3 times 10 to the 5 meters per second. Well, if you know kinetic energy is half mv squared, you can replace this Ke max into half mv squared, where the v will be the maximum speed if you're talking about the maximum kinetic energy. Okay, so phi is the minimum amount of energy to get to the surface. Some of the electrons will be deeper and they'll need more than that. So the ones which require the minimum amount of work, called the work function, to get to the surface are the ones that are going to get the maximum kinetic energy. But first you need to convert 4.75 electron volts into joules, and all you've got to do is to multiply the 4.75 by 1.6 times 10 to the minus 19, yeah, which is the conversion factor because it's the charge of the electron. So this is the charge, E, this is the voltage, V. When you multiply voltage, which is joules per coulomb, by the number of coulombs, which is the electron's coulomb charge, you get the energy in joules, okay? So this is how much energy 4.75 electron volts is in joules. So now we got the energy of the photon in joules. We know the work function in joules given to you here. So the difference between these two values is going to be the maximum kinetic energy. So the maximum kinetic energy is simply 1.3, the difference between the two values, which comes out to 1.3 times 10 to the minus 19 joules. And then you know that kinetic energy maximum is half mv max squared, which you equate to the difference in the energy we just talked about, and you square it, and you've got to square root it, so you'd have to do a square root sign here over this, yeah, and once you do that, you'll see it's 534,000, yeah, which is approximately equal to the value they've asked for, to two significant figures. So this to three significant figures, it's slightly over 5.3 times 10 to the 5 meters per second. And this is how you should show your answer, yeah? You should show that your calculated value is approximately equal to the value that they want, okay? And that's how you get your 3 marks, okay? Then, the next part of the question, the last part of the question, they want you to calculate the de Broglie. That's how you pronounce this. It's a French name. De Broglie is pronounced de Broglie, okay? Yeah, so de Broglie is this name, and you've done that before in electricity in Unit 2. I'm trying to highlight it for you. Can't highlight it right now. The de Broglie wavelength of the electrons moving at the two significant figures value. So they want you to use the two significant figures value, not your accurate value, okay? Calculate what it would be if it was exactly 5.3 times 10 to the 5, where there you just need to get the equation from the back of the sheet, which lambda equals Planck's constant divided by momentum. We know the velocity of the electrons, and the data sheet also gives you the mass of the electrons as 9.11 times 10 to the minus 31 kilograms. Multiply those two together, you get the momentum, and continue with the calculations I've shown it, and you can give your answer to three significant figures, because most of the data is three significant figures, but you should quote the final answer here to two significant figures. I always show my students that I've calculated it, oh dear, calculated it to three significant figures, and I put my answer there, and then over here I change it to two significant figures, because we only know that the electrons are moving at 5.3. We're not using 5.34. If they said use your accurate value, then here you could put 1.37. Okay, does that make sense? And there's your 13 marks. That's the penultimate question. And now the ultimate question, ultimate being the final. So I'm sorry, my PDF seems to have gone a bit askew. The photocopier must have got tired of me photocopying so many pages. A camera includes a 5-sided glass prism. I doubt it very much, but apparently it does. The diagram shows a ray of light incident on the prism. Here's the ray of light incident on the prism, okay? And the dotted line is called the normal. If you don't know that, it means you haven't been revising hard enough. You need to know that all angles are measured to the normal, okay? I still have students who are measuring, who are tricked by the fact that they give the angle to the boundary, yeah? And then they lose marks because of it, okay? That means you haven't done, what do I call it? I call it the donkey work. You've got to do the hard work to be able to be ready for exams. And my students who are listening to this will know who I'm talking about, that they make silly mistakes because they haven't basically worked hard enough on their notes. So the diagram shows that at the surface X, they've labeled surface X here, yeah? And surface Y is where we're going to go next, okay? So it's transmitted here to surface Y. They basically want to know what's going to happen at this junction. I've drawn this dotted line to make you realize that whenever you have any angles at a surface of the boundary, you need to draw the normal, okay? They've shown that it's not to scale, so you can't just simply measure it, okay? They don't want you getting your protractor out and measuring it. Explain why the ray of light refracts at surface X. What does refract mean? Well, at surface X, the ray enters an optically denser material in that glass is denser than air, okay? So when it does that, it causes it to slow down, yeah? So it changes direction towards the normal. I would put all this in, yeah? The examiners only put this point and this point down for the 2 marks, but you don't know what's in the mind of the examiner, so you've got to go the extra mile to make sure that you've got every key term he wants. So it changes direction towards the normal. Okay, remember, whenever refraction goes from a less dense material, from air into glass, for example, it bends towards the normal. So I would always add a third point if it's only 2 points, because maybe the examiner wants you to say what's happening, and depends on the examiner. You never know what they're giving marks for 100%. Okay, that's the 2 marks of the refraction. Now they're going on to talk about total internal reflection, which is at surface Y. The ray of light must be reflected. That's what they're telling us. We want it to be reflected. This reflection could be due to total internal reflection. So I put TIR, so I can then use TIR in my answer to know that they know that I know total internal reflection is the same as TIR. So I don't have to write it out completely. If the ray of light is not totally internally reflected at surface Y, yeah, the light can be made to reflect by applying a layer of silver to the surface metal. Well, that's basically changing the material from being glass into a mirror. If you put a silver surface on the back of glass, that's how mirrors are produced. You put a shiny material on the back of the glass and it becomes reflective. So if the angle is insufficient, and you'll see what I mean about angles I mentioned before. If the angle is not greater than the critical angle and total internal reflection is not going to take place, if you put a silvery surface there, it will reflect. Okay? Now, remember what I said? Students, if they think this is the angle of incidence here, it's not. It's the angle between the normal and the ray. So they're trying to trick you to use this 53 degrees. Now look at my answer. Okay. So they want you to deduce whether a layer of silver is needed to cause it to reflect or not. Well, the refractive index of glass that they've used, they tell you is 1.52. They give you this equation in the back. Sine of the critical angle is 1 over n. So we know that it would be 41.1. We know the angle they've given to us is 53. So we know the angle of the instant at y is not 53. It's 90 minus 53. Therefore, they want to see that you have converted it to 37 degrees. Well, obviously 37 degrees is not greater than the critical angle, so it's less than the critical angle for glass, so total internal reflection will not occur, yeah, due to the glass. So you need to put a layer of silver to cause the total internal reflection to take place, and that's 4 marks. All right, and then this is the part where I think most students wanted my help. Yeah, it is a more difficult question. It comes at the end. There's 2 marks here. Yeah. Oh, and then I had a blank page by mistake because I PDF'd it wrong, the last bit. And here is data. So 2 marks there and 5 marks here. So this is the most difficult 7 marks in the exam. So let's see what they're asking. It says the camera contains the light sensor. Okay. The camera can detect the number of photons each second on the sensor. Yeah, it detects the intensity of the light in some ways. Whether it can detect exactly the number of photons, I think that's what the question is getting at. Okay, in the part 2 over the page. The sensor has a known surface area. Okay, and so talking about intensity, and the intensity equation is this: intensity equals I over I. Intensity I is equal to power, joules per second, per meter squared. Okay, so that's why they're talking about surface area here. Yeah, so they know that they want to give you a clue that you need to use this equation in your answer. Explain why knowing the number of photons, yeah, on its own, arriving per second at the sensor cannot, yes, normally in English we make those 2 words stick together, but put this in bold. Cannot be used, yes, to determine the intensity of light. Well, remember the power is joules per second. The number of photons doesn't tell us joules per second. It just tells us the number of photons arriving. To be able to get the intensity, you need to know the energy of each photon as well. Okay, so this is basically how you get the 2 marks. Realizing this, it's basically a question about this, and then verbalizing your answer as I have done. Okay, I'll let you stop the video and reading it. So remember, the light sensor is basically converting the number of photons that comes in into a reading to detect how intense the light is. And now I say that because that's part 2, which is coming up after this blank sheet. Okay, so it says the light instant on the sensor causes a current. So in other words, it's actually measuring the current that is caused by the photons on the sensor. Okay, maybe not all of the photons activate release of an electron. So this is really the photoelectric effect in operation, and creating a technology that can be used to convert the photons into a current. Yeah? So I think there is a section of this in the photoelectric effect where you can stop the electrons emitted with a negative potential. Well, here we're just measuring the current, yeah? And for example, at the wavelength they give us, 600 nanometers, the current will be approximately 0.41 amps. So I didn't have a ruler with me, I'm sorry, when I was doing the answer. It comes to approximately 4.41 amps. So this is going to be used, this value. So it says that light with a power of 1.0 watts, two significant figures, remember, is incident on the sensor. So we have light coming in the form of photons and current coming out as an effect due to the sensor. So the sensor is a transducer. A transducer is a device that converts one form of energy, in this case radiation energy from photons, into electrical energy in the form of a measured current. The graph shows how the relationship between the wavelength of light, here, is connected to the current produced in amps. Okay, so that's the intro to this question, and you need this intro to be able to understand this question. The current is proportional to the number of photons detected per second. Yeah, well, I'm not sure that detected is right, but it's proportional to the number of photons incident on the sensor per second. Okay, so we have to do some working out. So we know they've already telling us that we have to use this graph by giving us the graph. Okay. Now it says monochromatic light. That means they're only using single frequency light. Monochrome. Mono means one, chrome means color. Yeah. And for physics, chrome means frequency or wavelength. So we're talking about 600 nanometers, which I referred to. Instant on the sensor. See, they said detected. I'm saying instant. Yeah. The current is proportional to the number of photons detected, yeah, although they're not all detected, and you'll see why on the sensor, because no device is 100% efficient. All right, so on the sensor, the power is given as 1.0 watts, which is 1.0 joules per second, and this is crucial, so we're talking about joules per second, yeah. And current is 0.41 amps or 0.41 coulombs per second. So if we just analyze everything as 1 second, you'll see that the current is going to be 4.41 coulombs if we're talking about 1 second. And you also know that current is made up of a number of electrons, and each electron has a certain charge. Okay, so we need to find out the number of electrons. Okay. Remember, each photon can release one electron. All right, so first of all, this is what I did. They want you to determine the percentage of photons that are detected by the sensor. So I told you, they haven't detected them all. We are only detecting a percentage of the photons with our inefficient sensor, or not 100% efficient sensor. So remember, I equals NE over T. If we use T as 1 second, yeah, we can work out N is equal to I divided by E. Yes? So we can then work out how many electrons have been, or correspond to 0.41. Yes? And we're talking about everything in per seconds. So that means we get 2.6 times 10 to the 18 electrons arriving or measured by this current. That's the equivalent of 2.6 times 10 to the 18 electrons in that reading. Okay? Remember, everything is per second, and that means it will make it easier for you. And the energy of a 600 nanometer incident monochromatic ray of light is equal to HF, as we talked about before in a previous question, which is the same as HC over lambda. So you change that, you get 1 mark from knowing that you have to change it to C over lambda instead of F. Put the numbers in, yeah. Here's C, here's lambda. Remember, nano is 10 to the minus 9. So make sure you know that you have to do that. 10 to the minus 9. You then get 3.3 times 10 to the minus 19 joules is the energy of the incoming photons. Okay? Now, again, Remember, we're talking about per second. And we know that the power is 1.0 watts or 1.0 joules per second. And therefore, that we also know power over energy is 1 over time. So power over energy is time. Energy, so I've reversed the energy. So power of energy is 1 over time. And this will tell us how many electrons, photons are needed to create this 1.0 joules per second. Remember, if we do it per second, then the answer will be per second. As therefore, you can change the equation round. If t is 1 second, n is equal to p over e, number arriving per second, and t is 1. So it's 1.0 divided by the energy of the joules. If you can't do this, you could do one more stage of here. Yeah? Remember, this is 1, so power equals energy for that. And the energy is n number of photons. It's not 1 photon. Okay, so you want to work out n, and this is the way of doing it. Okay, I probably could have put an extra step in there to make it clearer for some students, but then I would have run out of space. Okay, so once you do that, you'll get that that's going to be equivalent to 3.0 times 10 to the 18 photons, again arriving in our unit amount of time, and it will be this number. Now you see this number is how many photons are arriving, and this is how many electrons are being produced. Yeah? And this is the ratio of what is instant to what is detected. And that is basically the answer comes from these two numbers here. Okay? Incident, number of photons per second, giving off a certain current which is equivalent to number of electrons. Okay? So the efficiency of it, since the current is proportional to the number of photons detected per second, yeah, or I should say the number of electrons emitted by the photons detected per second, yeah, you can then work out the percentage of photons detected must be the corresponding of electrons emitted. Yeah, I think that's what it said. And I don't know what I've written here because it must have gone thing. The corresponding number of electrons emitted. Anyway, that should be enough. In a second, I think it should say. Yeah. Calculated number of photons arriving per second. So you divide this released electrons by the incoming photons and you get 87%. And there is the most difficult question of the paper for those of you who requested this. Sorry it's taken so long, but you know, I actually ran out of time as I'm working full time. So please do show your appreciation as I asked you at the beginning. Like, share, subscribe. Keep on inviting more people to come and see the work that we're producing, that I'm producing. No one else is helping me. And hopefully see you in the next video, and good luck in your exam on Wednesday, and please come and let me know how well you did in the exam on, is it Wednesday or Tuesday? I think the exam's on Tuesday if you're doing the International A-Level. Okay, thanks for watching. Bye for now. See you in the next video.